This unit consists of a bar of known hardness and a viewer and a hammer which has a ball and a plunger which you are supposed to hit to get an indentation in the unknown material, and one in the known bar. The relation of the diameter of the dimple will give us a value. Values like that is tabulated for steel, cast iron, and brass. The sloping end of the bar is only for easy insertion into the hammer, because there is a strong spring pushing the hammer down. The unit is photographed upside down. It shows the opening at the end that let the ball freely move and leave an impression in both pieces in the known and the unknown material. This is the viewer with adjustable lens and a little scale by millimeter from 0 to 8. By this viewer, we're supposed to measure the diameter of both dimples and the relationship between those diameter tabulated in values in a little booklet, and the values are for steel, cast iron, and brass. A hard object can transmit force, energy. Also, impact is energy. In this setup, the upper piece is a known steel, and the bottom one is the steel what we don't know the hardness of. There's a steel ball between the two. By hitting the top here, the ball will leave an impression in both pieces of steel, and by the relation of this impression of the diameters, a number can be established for hardness of the bottom piece. And this relationship is worked out in tables and given us. The individual diameter left in the pieces in the hard known piece and the unknown piece is irrelevant. Only the relation of one diameter to the other gives a value which can be used to establish some hardness for an unknown piece. Here I just drew up on AutoCAD something, and this is meaningless. It's just showing that I got a value of 1.5, but that doesn't mean anything. This will be a simple demonstration. Strong spring, I can hardly pull this spring. Since there is one trial at the very end, I go with this next to it. To know what is the hardness of this material, so I polished up one side a little bit. So we have our test piece here, and this prepared. The ball is between the two pieces. So now the ball between the two pieces here, hit it with a hammer. Now there is a little dimple in this one, and another dimple in that one. Well, the probe looks like has a smaller dimple, that means it will be harder. No, the other way around. The probe has a bigger circle. So the probe for the tested one will be harder. You have to measure the diameter of those two dimples. So I just make a circle around that piece, around that dimple. It's hard to see it. I can't see it with this viewer. I'm going to take a regular millimeter. That shows 2 millimeter. That one is 2.3. That the diameter of the impression left in the known probe is this value, 2.3. And the diameter of impression left in the unknown steel in millimeters, in the steel what we're examining is the number 2. This 97 is the yield strength in kilogram per square millimeter, and the red figure 272 is the number of the Brinell hardness, which I have no use for it. But once I know the 97, I can convert this from kilogram per square millimeter to psi, pound per square inch, which we use, or 1,000 pound per square inch, which is a kip per square inch, KSI. This little black book, handy little book, has a conversion table. Well, this is how it looks. Not that I ever gonna use it. I just gonna stick with my old methods, look at the spark, use a file, and decide that I keep on going or I'm going upstairs to have a nap. Well, some better are coming. Thank you for watching.